Page 163 from SciPAD. A flywheel has a length of string wrapped around it with a bucket of water attached to the string. The bucket is 1.05 meters above the ground. So that's our H or our D, probably a D. When released from rest, so we know that omega I equals 0 and VI equals 0, and it accelerates. It's talking about linear acceleration. Calculate the time it takes for the mass to reach the floor, and so we're going to be using a year 12 linear kinematic equation. I put them here, but you'll notice they're exactly the same as the angular ones, so I've just got linear things for it. And so we know that VI is 0, we know that A is given in the question is 2.75, we know the distance, D, and I'm looking for time. So I don't have VF, so I'm looking for an equation without VF in it, which is going to be this one here. So I've got D equals VIT plus a half AT squared. And I know that VI is 0, so that gets easier, and I'm looking for time, and so I can rearrange this like this to make it 2D divided by A square root it equals time. If you can't do that in your head, that's fine. You can just type it into Solver. So it's 2 times the distance, 1.05, divided by the acceleration, which is 2.75, and you square root that. You chuck that into your calculator, 2 times 1.05, and you'll need to do this as separate lines or put that top line into the brackets. You should get a time of 0.874 seconds, which is much longer than it would be if you just dropped it. And so that tells you that there is a force in the opposite direction. Okay, B, you're going to use A equals R alpha, and it says calculate the angular acceleration. So you're looking for alpha equals A over R. That linear acceleration is 2.75. The radius is 0.58. So 2.75 divided by 0.58 is going to give you 4.74 radians per second. Find the angular velocity of the flywheel at the instant that it reaches the floor. So what do we know? We know the initial angular velocity is 0, because up here it says it started at rest. We know the angular acceleration because we just worked that out. Theta, do we know the angular displacement? Well, we know distance from up here, and so I can use this equation, D equals R theta. So theta equals D over R. So it traveled 1.05 meters, and it did that with a radius of 0.58 meters. And so 1.05 divided by 0.58 tells me it's done 1.81 radians. And the thing I'm trying to find out is omega F. And so I'm looking for an equation that doesn't have time in it. And so if I look at my formula sheet, which one doesn't have time? Omega F squared equals omega I squared plus 2 alpha theta. And because I know that is 0, that makes it simpler. I can just say the final speed of what I'm looking for equals the square root of 2 times the angular acceleration, 4.74, times the angular displacement of 1.81. If we chuck that into our calculator, 2 times 4.74 times 1.81, square root answer, gives me an answer of 4.14 radians per second. Okay, moving on to D. Calculate the weight, net, and tension forces acting on the bucket of water. Okay, so weight force is mass times gravity, and so 2.85 kilograms is quite a significant bucket of water. 2.85 times 9.8 1 gives you 27.959 newtons, not the correct number of figures. The net force, well, the net force is going to be this acceleration of 2.75. So mass times acceleration is 2.85 times this one here of 2.75, which gives you a force of 7.83 newtons. And so what's the tension force? Well, there's a large force downwards, and the net force is that, and so there must be a tension force up, which must be the difference between these two. And so I'm going to subtract them. So I'm going to go 27.9585, take away 7.8375, and that's going to be 20.1 newtons. So then it says calculate the size of the torque, and so we know that torque equals force times distance, or force times radius, and so there's a 20.1 Newton force acting at a radius of 0.58. Times 0.58 gives you 11.67 Newton meters of torque. And then if we want to work out the rotational inertia, torque equals I alpha, so I equals torque divided by alpha. And if we've got 11.67 newtons meters of torque, and that's causing an acceleration of 4.74, then we can divide that by 4.74, and we get 2.46 kg meters squared of rotational inertia. Cool. Question 3, a 295, so 0.295 mass is tied to a string, which is then passed over a pulley attached to a turntable, as shown in the diagram. The central shaft here has a diameter, so a radius of 0.08 meters, because we're only looking at radius. The mass is initially held stationary, so the initial velocity is 0, 0.85, distance, which equals height, which equals 0.85 meters above the ground. When released, the mass accelerates downwards, reaching the ground after a time of that. Calculate the angular acceleration of the turntable. So I've just grabbed a formula sheet, and we look at the things that we know. So we know that VI equals 0. We know that it's accelerating, and that's essentially what I'm trying to find out. We know that time equals 0.79 seconds, and we know that the distance equals 0.85 meters. And so I'm looking for an equation that doesn't have VF in it. So I'm going to be using the same equation, D equals VIT plus a half AT squared. Because once I know acceleration, and because I know the radius, I can therefore work out the angular acceleration. Like before, because it started off at 0, that makes that whole part of the equation really easy. And if I'm solving this for A, then it's going to be 2 times distance divided by time squared. It's going to give me A, which is going to give me 2 times the distance, 0.85, divided by time squared, 0.79 squared. So you would do the top line of brackets, so 2 times 0.85, close bracket, divided by 0.79 squared, gives me an answer of 2.723 meters per second. And it did actually say calculate the angular acceleration. And so if I'm looking for the angular acceleration, I'm going to use A equals R alpha, and therefore alpha is going to equal A divided by R, which is going to be 2.723 divided by the radius of 0.08, which is half of the 0.16. And that gives me an answer of 34 radians per second, which is pretty fast, but that is the correct answer.